Okay, hi everyone. Thanks for coming to our second math club meeting. Today I wanted to lecture on expected value because if you're doing UIL math or AMC or AME or whatever math competition you're doing, expected value is definitely something that you have to know. So the expected value of a random variable x is equal to the sum over all outcomes of the value of the outcome times the probability of that outcome. Written in symbols, this is the following. Now I wanted to make a note about something. This is one way to write the definition of the expected value. X times the probability of x, the sum over all x. A is the set of all possible outcomes. But you actually don't have to write the x's in A, right? Because I claim that if you don't write the x's in A, I claim that these are equal. Because if x is not in the set of possible outcomes, then the probability of it happening is just 0. So that term would disappear anyway. So that's why you don't have to write this x in A. So just use the example. If x is the result of a fair dice roll, then what's the expected value of x? You can just say it. 3.5? Yeah. Just so each one has probability 1/6. You add up all of them and divide by 6 to get the expected value. Okay, so for any two random variables x and y, the expected value of x plus y is equal to the expected value of x plus the expected value of y. This is always true for any random variables, and it's called linearity of expectation. This is the most important rule. So let's try. If you flip 10 coins, what's the expected number of heads? Yeah. So this problem is really easy. That it's pretty obvious that the answer should be 5 based on your real life experience. But the point of this example is to understand where this comes from, starting from the definition of expected value. So I actually want to go in reverse order. Can we go to we skip one slide?
This one?
Next one, after this. Okay, so if you advance it a little more. Thanks. Let's introduce 10 helper random variables. Let xi be 1 if ith coin comes up heads and 0 otherwise. So now you have 11 random variables. You have x1 through x10. They all take values that are either 0 or 1 based on whether the ith coin comes up heads. And then we have h, which is equal to the total number of heads. And it's by definition equal to x1 plus x2 plus ... plus x10. And we want to find the expected value of the number of heads. So we want to find expected value of h. And we know that h is equal to this. And by linearity of expectation, we can say that this is equal to expected value of x1 plus expected value of x2 plus expected value of x10. So now we just have to find what expected value of x1 is, and the other ones will be the same. But we know that the expected value of x1 is just the expected value of a single coin coming up as heads. And we know that the expected value of one head is 1/2. So you can multiply it by 10 since there's 10 identical random variables, and it equals 5. So that's how you prove that the expected number of coins which come up heads is 5.
Forward or back?
Forward. This is another example of linearity of expectation. And you should try it, and you can tell me what answer you get. do you get?
Is it 25?
Yeah. Let's consider let's consider one chick, and we want to calculate the probability that it won't be packed. So it won't be packed if this person decides to go left and this person decides to go right. I don't care which direction this guy packs. I just care that this one doesn't pack it and this one doesn't pack it. So the probability that a chick isn't packed is the probability that this chick packs left and this chick packs right. So the probability is 1/2 times 1/2, which equals 1/4. And the expected value of the number of chicks who get packed is just the sum of all those expected values by linearity of expectation. So the expected value of the number of unpacked chicks is 100 times 1/4, which equals 25, like Jason said. Okay, well, harder example. So you have two numbers, A, B, and C, D. The way we choose these numbers is that we take the numbers 1, 2, 3, 4, and we randomly assign them. So you can assign 2 to A, 1 to B, 3 to D, 4 to C, for example. They're just assigned at random. We have to find the expected value of the product of these two numbers. Try it and see what you get. What's the first we can say that AB, we can write the value as 10A plus B. We can also say that for CD, we can write the value as 10C plus D. So then the product of the two numbers would be 10A plus B times 10C plus D. Okay. Did anyone get an answer? Okay, what we do after this is that's okay, we can apply linearity of expectation. We can find expected value of AC, which is just the product of A and C. Yeah, so we want to find expected value of the product of the two numbers. We can write the product like this. Now if we open the brackets, we get expected value of this expression. And we want to take, which is the same as the expected value of this expression. By linearity of expectation, we can rewrite this as 100 times the expected value of AC. We can rewrite it as this. So we just need to find what the expected value of AC is, right? Because the expected value of AD is the same as the expected value of BC, BD. They're all the same because A, B, C, D are symmetric. So let's just find the expected value of AC. You can go to the next slide. We can make a table with all of the possible values. So on the rows, I have the values of A. In the columns, I have the values of C. In each cell, I wrote the product of the row index and the column index. we should ignore this diagonal because those are the values where A equals C. Remember that A is not allowed to be equal. A and C have to be different. Now we calculate this. Now each of these has probability 1 over 12 because there's 4 rows and there's 3 valid entries in each row. So each value has probability 1/12. So the expected value would be each of them times 1/12. You add them all up. If you add them all up, you get 70, and you divide it by 12, you get 35 over 6. And that's the expected value of AC. So can someone tell me the answer now? If the expected value of AC is 35 over 6, what's the expected value of the product? Remember that we said the expected value of the product is just equal to the expected value of this thing, which is equal to
121.
yeah. Okay, so you have 100 plus 10 plus 10 plus 1 times the expected value. But these are all the same. They're all 35 over 6. So you can just take the coefficient, 100 plus 10 plus 10 plus 1, and multiply it by the expected value. So you take this, you multiply by 121, and you get the expected value of the product. Okay. So linearity of expectation is definitely the most important one that shows up the most. But there are also some more obscure tricks that are also good to know. For if x and y are independent, then the expected value of x times y is equal to the expected value of x times the expected value of y. So x and y are independent if knowing the value of x doesn't affect the expected value of y. So I want to do an example that's not on the board. Let's say that x represents the value of a dice roll. What's the expected value of x? 3.5. What's the expected value of x squared? The whole thing squared. So 3.5 squared. What's the expected value of x squared? So you cannot use this formula here because x and x is not independent. If you know the value of x, you know the value of x. This is only true if x and y are independent variables. X is not independent with itself. So this does not apply. In order to find the expected value of x squared, we need to look at all the possibilities. Each one has probability 1/6, and it would be like 1 squared plus 2 squared plus 3 squared plus 6 squared. Because every single event has probability 1/6, so it's like 1/6 times the value of the first event, 1 squared, plus 1/6 times the value of the second event, 2 squared, 1/6 times 3 squared, plus, and so on. Anyone know what this is?
91%.
Okay. Also, if you are taking statistics, you can know that the variance of x is equal to the expected value of x squared minus the expected value of x squared. But that's just a tangent. Now we'll actually use this identity for independent random variables on the next problem. This is like inflation. A TV originally cost $1,000. Every day the price increases by either 1% or 2%. Each has probability 1/2. Find the expected final price. Okay, so try it and tell me what you get. Yeah.
1,160.4.
How did you do it?
Geometric mean this have 10.
Wait, you took the geometric mean of 1.01 and 1.02? No, it's not right. Okay, let's just start by introducing some variables. Let the final price of the TV be x, and let's introduce 10 helper variables, x1, x2, and so on. Oh, I called it A. So AI is equal to 1.01 or 1.02, each of them with probability 1/2. So what's the expected value of AI? Both of them are equally likely. Yeah. Then we can write that x is equal by definition to 1000 times A1, A2, A10. Agree? So we want to find the expected value of x. This is equal to the expected value of 1000 times A1 times A2, A10. And this is equal to the expected value of A1, A2, A10, added to plus A1, A2 through A10, added to itself 1000 times. Agree? So then we can say that this is equal to the expected value 1, A2. Expected value of the product of all the A's. So we just have to find the expected value of A1 times A2 times A10. But as you can see, this, you can say that expected value of A1 times A2 times A10 is equal to expected value of A1 times expected value of A2 times expected value of A10. Because of that identity on the previous slide, expected value of xy equals expected value of x times expected value of y, if x and y are independent. Here, every single AI is independent from the other. If the price increased by 1% on the first day, it doesn't mean that it's more likely to increase by 1% on the second day. Each of them is independent from each other. They're all equally likely every day. So that's why the final price is equal to 1000 times 1.015. That expected value we calculated in the beginning to the power of 10, because there's 10 days. I give you one definition of expected value. Here's an equally valid definition that is also that's the same, but this one can be more useful sometimes. We can view the expected value as an average. The sum over all events of the value of x over the sum of all events of 1. So a permutation of 1 through n is chosen at random. What's the expected number of fixed points? So let's say n equals 5. And let's say a permutation. A permutation is the numbers 1, 2, 3, 4, 5 scrambled in a random order. A permutation is any rearrangement of the numbers 1, 2, 3, 4, 5. So one possible permutation might be like this. And a fixed point is a position such that it's equal to its position. So 3 is in the third position, and its value is 3. So that's why it's a fixed point. There are no other fixed points here. 1, 2, 3, 4, 5 would have all 5 of its numbers as fixed points. And I want you to find the expected number of fixed points in a random permutation. let's calculate it by hand for some small values of n. For n equals 1, what's the expected number of fixed points? Yeah, because there's only one permutation, right? And that one permutation has one fixed point. So for n equals, let's make a table. One is 1. What about 2? It's 1, 2, 2, 1. This has 2, this has 0. The average is 1. What about 3? You can just write out all 6 of them. Or you can make a guess based on the table.
1.
Yeah. Okay, let's prove it for general n. Let's say that the expected number of fixed points is equal to the average number of fixed points. So the average number is just the total number of fixed points across all permutations over n factorial, the number of permutations. Okay, so how do we count the total number of fixed points across all permutations? I'm going to count the contribution of a single position. So let's say that like I'm writing a permutation of length n. So there's n spaces here. My plan, in order to count the total number of fixed points over all permutations, is going to be counting how many permutations have a fixed point here, and then adding how many permutations have a fixed point here, and so on. And if I add those numbers all up, then I'll get the total number of fixed points across all the permutations. So how many permutations have a fixed point here? That means this is equal to 1.
At least 2.
It depends on n, right? N minus 1 factorial, yeah. Good job. Because you have to put 1 here, but the other ones can be distributed in however you want. N minus 1 factorial ways. So no matter which cell I fix as a fixed point, so like if I force this to be a fixed point, then it has to be 4. But the other ones still can always be distributed in n minus 1 factorial ways. So if we add this up over all n cells, there's n cells and each of them contributes n minus 1 factorial to the sum. So the total is n factorial. The total number of fixed points across all permutations is n factorial. Therefore, the expected number of fixed points is equal to n factorial over n factorial is 1. That's a proof. So as you can see, we found a much easier solution to the problem by interpreting expected value as an average. I have one last problem. It's pretty hard. Devin, you should try it. Ten numbers are chosen uniformly from 0, 1. Let m be the maximum. Find the expected value of m. So like, let's say that I just choose 3 numbers, just to give an example. You choose 0.3, 0.5, then the maximum is 0.7. And like these numbers are chosen randomly from 0 to 1. There's 10 numbers. What's the expected value of the maximum?
Does the uniformly mean like equally spaced?
Yeah, so
Yeah,
I have like,
definitely.
0, 1, and I'm just going to close my eyes and choose any point. And I close my eyes, choose another point, and do it 10 times. What's the expected value of the rightmost
So
one?
they don't.
You can give me some guesses on what it is, if you want. It's greater than 1/2, right? Because I'm taking the maximum over many different tries. 10 11s? Yeah. Okay, let's see how to do it. We're going to define P of x so that P of x dx is the probability that m is between x and x plus dx. So let's say that each of my guesses are x1, x2, x3 through x10. P of x is equal to the probability that the maximum is here. So exactly one of these 10 needs to be between x plus dx, x and x plus dx. And the other ones all need to be less than or equal to x. They all need to lie in 0x. So there's 10 ways to choose which one lies here. And that one only has dx over 1 probability. The other ones all have probability x over 1. And there's 9 others. So this is the probability that the maximum is between x and x plus dx. And we can check that we have the correct function p of x. So this is p of x because you just divide the dx, get rid of the dx, because p of x dx is the probability that m is here. So p of x, you just get rid of the dx. P of x equals 10x to the power of 9. We can check that this probability distribution function, p of x, is correct by integrating it from the bounds of x. In this case, x is from 0 to 1. So if we integrate it, we should expect to get 1. Like, for any probability function, the sum of all the probabilities is equal to 1. So for the same analogous thing for probability distribution functions is that if you integrate p of x dx, you should also get 1. P of x was 10x to the power of 9. If we integrate it, it's like 10 times x to the power of 10 over 10. This is 10. Oh, sorry, it's 1. 10 times 1 over 10 minus 0, which equals 1. So our probability function p of x is correct. Okay, so now we just need to say that the expected value of x is equal to the sum over all x of x times the probability of x. And the equivalent formula for, I will write the equivalent formula. If we want to write it, this is when x is a discrete random variable. There's only a finite set of possibilities that x can be. But here we're working with a continuous random variable. X can be any number between 0 and 1. There's an infinite number of values that x can take. So in this case, the expected value of x is equal to, replace the sum with an integral, and replace p of x with p of x dx. So that's the expected value of x here. Remember that p of x was equal to 10x to the power of 9.